Good morning, guys. So we will continue our previous problem. Means in previous lecture we discussed one problem, or we have solved one problem up to the elemental stiffness matrices. Okay, this was your problem. Means there are three elements, 1, 2 and 3. At this node there are two forces. One is 20 kN acting in downward direction and one is 15 kN acting in horizontal direction. Similarly, there is a fixed support and there is a roller support. Okay, so up to this means up to this elemental stresses we have discussed, or we determined these elemental stresses. Okay, it's not stresses, elemental stiffness matrices. We determine our elemental stiffness matrices for each element. Okay, so this is K1, this is K2 and this is K3. Okay, so we determine elemental stiffness matrices for element 1, 2 and element 3. Now the next step is what? To find out or to construct the global stiffness matrix by using this elemental stiffness matrix. Okay, so as we know that there are three nodes, 1, 2, 3. So first we need to decide the order of the global stiffness matrix. So what will be the order of the global stiffness matrix? So to decide the order of global stiffness matrix, we have a formula. So what is this formula? Number of nodes into degrees of freedom at each node. Okay, so we know this formula. N is equal to number of nodes into degrees of freedom at each node. So as there are three nodes, 1, 2, 3. So 3 into now degrees of freedom at each node. So we know that at each node there are 2 degrees of freedom. First one is displacement in horizontal direction and second one is displacement in vertical direction. So degrees of freedom at each node will become equal to 2. So 3 into 2. So order of that global stiffness matrix will become equal to 6. Okay, so this is the order of your global stiffness matrix. Why? Because at each node there are 2 degrees of freedom. First one, it is in first displacement, it is in horizontal direction. Second displacement is in vertical direction. So there are 2 degrees of freedom at each node. Now next is what? So construct the global stiffness matrix by using these 3 elemental stiffness matrix and of order 6 by 6. Okay, so now we will construct the global stiffness matrix of order 6 by 6 here by using these 3 elemental stiffness matrices. Okay, so our global stiffness matrix will become of order 6 by 6. So here I am writing this global stiffness matrix. Okay, so 6 by 6 means what are these displacements or what are these connectivities of these 3 elements? So U1, V1, U2, V2, U3 and V3. Okay. Similarly, U1, V1, U2, V2, U3, V3. This is the connectivity of the global stiffness matrix for these 3 elements. So we need to construct the global stiffness matrix. K is equal to now. So to construct the global stiffness matrix, we will use the elemental stiffness matrix. So first one, this is the elemental stiffness matrix for first element. So put this elemental stiffness matrix or connectivity between U1 V1, U2 V2. As we know that this element, it is this connectivity of this element is in between node 1 and 2. It means between U1 V1, U2 V2 rows and also columns. So put this matrix over the global stiffness matrix. Okay, so U1 V1, U2 V2. So U1 V1, U2 V2. It means this is the first elemental stiffness, position of the first elemental stiffness matrix. Now next is what? K2. We need to place this K2 over the global stiffness matrix between rows and columns. Which are the rows and columns? U2, V2, U3, V3 and columns U2, V2, U3, V3. So it will start from U2, V2, U3, V3 means this will start from this one. So this point to last one this. Okay, so you need to place this global stiffness, elemental stiffness matrix, second elemental stiffness matrix over the global stiffness matrix by this over these positions. Okay, now next is what? Third. The third element, the connectivity of third element is in between node 1 and 3. It means between rows and columns. Which rows and which columns? U1 V1, U3 V3. So U1 V1, U3 V3 rows and U1 V1, U3 V3 columns. So U1 V1 is, these are the positions. Okay, these are the positions for third elemental stiffness matrix. Okay, U3. Okay, so in this way you can put this third elemental stiffness matrix or global stiffness matrix at these positions. Okay, because we know that the connectivity of third elemental stiffness matrix is in between node 1 and 3, means U1 V1, U3 V3 rows, similarly U1 V1, U3 V3 columns. So now we will put these three elemental stiffness matrices or these elements over global stiffness matrix. So now first elemental stiffness matrix. This is your first elemental stiffness matrix. The position is between U1 V1 U2 V2. So put this between U1 V2. So 100 0 minus 100 0, then 0 0 0 0, then minus 100 0 100 0, and finally 0 0 0. Then next one is between position U2 V2, U3 V3, this second elemental stiffness matrix. So it will start from U2 row, U2 column. So from this point it will start. So first row is 0 0 0 0. So first row is 0 0 0 0. Now second row is, it will start from row V2. Okay, and this column U2. So V2, it will start from row V2 in column U2. So from this point it will start. So this is 0 plus 130, 133.3, then 0 minus 133.3. Then next, third row, 0 0 0 0. So it will start from U3 row and U2 column. So 0 0 0 0. Finally V3 row, and it will start from U2 column. So 0 V3 row and U2 column. Is it? It is 0 0 minus 133.33 0 and plus 133.30. In this way, the second elemental stiffness matrix is positioned. Okay. Now next is what? Third elemental stiffness matrix. We need to position. We need to map this matrix over the global stiffness matrix. Now, so first row is U1. So U1 first row, and it will start from which column? U1 column. So U1 row. This will start from this U1 row, U1 column. The value is 51 plus 51.2. Then U1 row, V1 column 30. U1 row, V1 column 38.2 plus 38.4. Then U1 row, U3 column. U1 row, U3 column. So this is the value minus 51.2. Then U1 row, V3 column. U1 row, V3 column. So this is the position minus 38.4. Then next, V1 row, U1 column. Here V1 row, U1 column. So this is the point. So 38.4 plus 38.4. Then V1 row, V1 column. V1 row, V1 column. So here is the position. So plus 28.8. Then V1 row, U3 column. This is the V1 row and U3 column. This is the position. So minus 38.4 and finally minus 28.4. So 28.8. Okay, then next U3 column, U3 row, sorry, U3 row, U1 column. So here U3 row is here and U1 column and U1 column. So this is the position. And what is the value? Minus 51.2. So minus 51.2. Then U3 row, V1 column. U3 row, V1 column. This is the position. Minus 38.4. Then U3 row, U3 column. Here U3 row, this is the row and U3 column. So here is the position. 51 plus 51. Then U3 row, V3 column. Here is U3 row and V3 column. This is the position. 38 point plus 38 point. Then V3 row, U1 column. V3 row, U1 column. Means first, these are the first two positions. Minus 38.4, minus 38.4 and minus 28.8. Minus 28.8. Then next, V3 row, U3 column. So V3 row, U3 column. Here is the position. 38.4 plus 38.4 and plus 28 point plus 28 point. So in this way, you can map elementary stiffness matrices over global stiffness matrices. Okay. So in this way, you will get the global stiffness matrices. So on simplification, we will find out final. We will determine the final global stiffness matrix. Okay. So on simplifying, okay, so this will become 100 plus 51.2. This will become 151.2. 151. So this will become 38.4. 100, 0 minus 51.2, 38.2. Then this will become 38.4. This will become 28.8. Okay, 100, 0. This will become 100. This is 0. Okay, then 0. This will become 0. Then 133.3. Then 51.2, 38.4, then 38.4, and this will become 162.30. 3 plus 0, 3, 8 plus 3, 11, 1, 1, 8 plus 1, 1, 9, 9 plus 3, 12, 1, 2 plus 1, 3, 3 plus 3, 6, 162.30. 162. In this way, you will get final global stiffness matrix. Okay. So cross check whether this global stiffness matrix is correct or not. So to cross check, this is your diagonal. Okay. Check whether this matrix is symmetric about this diagonal or not. So check 38.4, 0, 0, 0, 38.4. 38.4, 0, 0, 0, 38.4. It means it is symmetric. So minus 100, 0, 0, 133. So minus 100, 0, 0, minus 133. Similarly, 0 minus 38.4, 0. 0 minus 38.4, 0. Similarly, minus 51.2, 28.2. Minus 51.2, 28.2. And last one is 38.4, minus 38.2. So it means it is symmetric. Okay. So we conclude that it is correct. Okay. So in this way, you will get the final global stiffness matrix. Okay. So Now next step is what? This is the final global stiffness matrix. So we will write down this global stiffness matrix in a. So this K will become equal to U1, V1, U2, V2, U3. This is your U1, V1, U2, V2. So we will write down this global stiffness matrix column wise. So 151.2, 151.2, 38.4, minus 100, 0, minus 51.2, minus 38.2. Then next V1 column, so 38.4, 28.8, 0, 0, minus 38.4, minus 28.8. Then next U2 column, minus 100, 0, 100, 0, 0, 0. Then V2 column, 0, 0, 0, 0, 0, 133.3, 0, minus 133.3, minus 133 point. Then next is U3. U3 column, minus 51.2, 38 minus 38.4, 0, 0, 51.2, 38.4. Finally V3, minus 38.4, minus 28.8, 0, minus 133.3, 38.4, 162.30. In this way, this is the final global stiffness matrix. This is the final global stiffness matrix. Okay. So now next step is what? This is your final global stiffness matrix K. So next step is what? Write down the displacement and force relationship. So we know that displacement and force relationship is written as F is equal to this global stiffness matrix into your global displacement vector. As we know that, so this our problem statement is that this is the problem statement. Okay, so this is your problem statement. So this is fixed one, this is roller support is there. Okay, so as we know that for first node U1, V1, these are the displacements. Similarly, F1x, F1y, these are the forces. At second node U2, V2, these are the displacements. Similarly, F2x, F2y, these are the forces. And at third node, this is your U3, V2. Similarly, F3x and here F3y. These are the forces. So in this way, to write down the force and displacement relationships, we need these displacements and forces. So we will write down these relationships now. So this is your F1x, F1y, F2x, F2y, F3x, F3y. Okay, this is your force vector, is equal to global stiffness matrix into displacement vector. So displacement vector will become U1, V1, U2, V2, U3, U2. Okay, so in this way you can write your force and displacement relationship. Now, next step is what? So next step is, okay, so in this way you can return, you can write the force and displacement relationship by using this global stiffness matrix. Okay. Now next step is what? Apply the boundary conditions. Okay, so to apply the boundary conditions, as we know that this is our problem statement. This is fixed one. There is a roller cell. Force of 20 kN is acting in downward direction, and force of 15 kN is acting in horizontal direction. As we know that this is U1, this is V1, U2, V2, U3, V2. Similarly, F1x, F1y, F2x, F2y, F3x is nothing but 50 kN, and F3y is nothing but equal to minus 20 kN. Okay, it is E1. So apply the boundary conditions for displacement first. So as we know that this node is fixed node. Okay, this node is fixed one. So displacements at these nodes U1 and V1 will become equal to 0. So U1 and V1 will become equal to 0. Then at this node, at second node, there are two displacements U2 and V2. But due to this roller support, it will restrain the displacements in y direction. Okay, there is possibility of displacements in x direction only. Because of this roller support, maybe this support will displace by this amount equal to u. Okay. Due to this load, this node will displace by some amount in horizontal direction, but in vertical direction it is restrained due to this roller support. Okay, so there will not be any vertical displacements at this node 2. Due to this, V2 will become equal to 0 and F2y will become equal to R2y. Okay, because there must be a vertical reaction. So vertical force we have assumed F2y, so it is nothing but equal to R2. So V2 is equal to 0. Why? Only horizontal displacements will occur in horizontal direction, but there will not be any vertical displacement due to this roller support. So V2 will become equal to 0 and U2 it is unknown. Means we need to find out this U2 value. How much amount of displacements will occur in horizontal direction at this node due to this force 20 kN or 50 kN. Okay, so there will be some displacements will be occur at node 2 in horizontal direction, which is nothing but equal to U. So U2 is the question. So U2 is unknown. Okay, so this is unknown value. Here we need to find it. Now V2 is equal to 0. Okay, V2 is equal to 0. Similarly, U3 and V3. So this is there is no support at this node 3. This is free one. So there will be some displacements in horizontal as well as in vertical direction. So U3 is also unknown and V3 is also unknown. So we need to find out U2, U3 and V3. So Okay. Similarly, apply the boundary conditions for forces. So forces F1x, it is nothing but your R1x. It is the reaction. Similarly, F1y, it is nothing but your R1y. It is the reaction. Now F2x. Now F2x, the value of F2x is not given, so it is assumed to be 0. But F2y it is nothing but your support reaction. R2y, it will become R2. So this will become R1x. This will become R1y. F2x is equal to 0. This will become your R2, and F3x is equal to Q1. F3x is nothing but 15 kN. F3y is nothing but minus 20 kN. So F3x is equal to 15 kN and F3y is equal to minus 20 kN. So in this way, we have applied all the boundary conditions for displacements as well as for forces. Now, next step is what? Elimination approach. So as we know that, find out the displacements whose value is equal to 0 and eliminate these rows and columns. Okay. So here U1, V1 and V2 values are 0. So eliminate U1 row, U1 column, V1 row, V1 column, similarly V2 row, V2 column. So U1 row, U1 column. So we will eliminate these rows and this column. Similarly, V1 row and V1 column. Similarly, V2 row and V2 column. Okay. V2 row, V2 column. So remaining terms are, this equation is remaining, third equation is remaining, fifth equation is remaining, sixth equation is remaining. So remaining terms are, these are the remaining terms. Okay. So these are the remaining terms. These are the remaining equations. So we need to write down these remaining equations. So remaining equations will become F2x is nothing but 0, 15 and minus 20 is equal to, this is nothing but equal to, so 100, 0, 0, 0, 21.2 and 38.4, then 0, 38.4 and finally 162.30 into U2, U3 and V3. Okay, so these are the remaining three equations. After elimination, you will get these three equations. Now you can solve these three equations by using Gauss elimination method, or directly you can solve these three equations by using three unknowns in your calc, and finally you will get the values for U2, U3 and V3. So you will get values for U3 as, finally you will get values of U2, U3 and V3 by putting these three equations in your calc for three unknowns. You will get these three values, U2, U3 and V3, or you can solve these equations by using Gauss elimination approach also. Okay, so you will get final answer as U2 is equal to, so finally by solving these three equations, you will get final answer as U2 is equal to 0, U3 is equal to 0.46 mm and V3 is equal to minus 0.23. Okay, so in this way you will get these three displacements, U2, U3 and V3. Now next step is what? So these are the displacements. So now next is what? To find out the stresses in each element. So we know that to find out the stresses, we know that the formula sigma 1 is equal to E1 by L1 into minus L1 L1 M1 into, for first element the connectivity is in between node 1 and 2. It means the connectivity between node U1 V1 U2 V2. Okay, so by using this stress formula you can find out the stress value. Okay, so stress value is equal to, so sigma 1 by putting all these values. Now L1 M1 L1 M1, this is nothing but cos theta sin theta. These values you will get from first table because we determine all these values. Okay, so you will get L1 M1 L1 M1. Similarly U1 V1 U2 V2. These values are known because U1 V1 0, U2 is also 0, and V2 values taken from this. Sorry, V2 is equal to also 0. U2 is also 0. So this will become sigma 1 value will become 0. So sigma 1 value is equal to, so sigma 1 is equal to 0. Next sigma 2. Sigma 2, so formula will become E2 by L2 minus L2 minus M2 L2 M2 into the connectivity of the second element is in between node 2 and node 3. So it is nothing but U2 V2 U3 V3. So put L and values from first table for second element and put the displacement values. So U2 is equal to 0, V2 is equal to 0. Now U3 value is 0.46 and V3 value is minus 0.26. Or by putting and by multiplying this, you will get sigma 2 as sigma 2 value is equal to 0.15 0.01533 kilonewton per mm square. So finally this will become in megapascal. It will become 15.33 megapascal. Okay. And similarly for sigma 3, E3 by L3 minus L3 minus M3 plus L3 M3 into, now the connectivity we know that between node 1 and 2, so U1 V1 U3 V3. By putting all these values you will get sigma 3 equal to 9.2 into 10 raised to the power minus 3 in terms of kilonewton per mm square. In terms of megapascal, 9.2 megapascal. Okay. And finally, reactions. So for to find out R1x, use these first equations. To find out R1y, use this second equation, and to find out R2y, use this third equation. So by using this 1, 2, 3 equations, you will get these 3 values, and these 3 values I will give you the answer only. You try to solve these 3 equations. You just need to multiply this first row into this column. You will get R1x. Similarly, if you multiply second row to second column, because all these values are known, you will get second value. So these values are R1x is equal to minus 14.72 kilonewton. Then R1y is equal to 11.04 and R2y is equal to 13.65. You can cross check by using these force balancers, because we know that this is minus 20 kilonewton, this is 15 your R1x, sorry, R1y, and this is your R1x. Okay, one second. So by solving these three equations, you will get these three values, R1x, R1y, and R2. So you just need to cross check. As we know that this is 20 kilonewton, this is 50 kilonewton. Okay. And we know that this is your R2y, this is your R1y, and this is your R1. So R1x is nothing but minus 14.70. R1y is equal to 11.04 and R2y is equal to 30. Sorry, R1y is equal to minus. This is minus. And R2y is equal to 30.65. So to keep this structure in equilibrium, the force balance must be there. So this force is balanced by this force. Look at this round figure. You can take it is equal to minus 50 kilonewton. So this force is in this direction, positive direction, and this force is acting in opposite direction, means negative direction. So this is balanced. Now for vertical balance. So this minus 11.04 plus 13.65. It means 30 minus 11, 19 point something. So it means round figure 20 kilonewton of force is acting in vertically upward direction. Similarly, 20 kilonewton of force is acting in vertically downward direction. It means this is balanced. So it means your example, your answers are correct, displacement values are correct, and due to this, if the displacements are correct, you will get this force balance. So your all answers means displacement, stresses, and reactions are correct. Okay. So in this way, you will get the displacement, stresses, and reactions. Okay. So here we will conclude our lecture. Means we determine all the values related to your stress element by using same procedure that we have applied for spring as well as for bar element. Okay. So here I am concluding this lecture, and in next lecture we will try some another examples related to your truss element. Okay. So thank you.